In this video, I'm going to explain the Doppler effect. This is part of topic 9.5 of the IB/HL Physics syllabus. It is not required then for SL Physics. Please take a moment to read through the success criteria that I plan to cover in this video. One of the things I like to show in my class is a video from the Big Bang Theory, and according to Sheldon, this is what the Doppler effect is. It's the apparent change in the frequency of a wave caused by the relative motion between the source of the wave and the observer. And in the picture here, you can see that this is his interpretation of the Doppler effect for his Halloween party. One of the other things I show in my class a lot are the animations from the University of New South Wales. I've written the link there. They have a whole series of waves and how they are affected, and they've got a really good one on Doppler. I really like this example that they do about seeing two surfers on a wave. Some of the math they do isn't quite needed for our level, but I really like this example. So let's think about this. They've got two surfers sitting on top of the wave, and if they're not moving, in other words, if there's no relative motion between the two of them, they're just going to go up and down at the same frequency. Now let's consider the second surfer moving towards the first. Now we have a relative motion between the two of them. What these numbers are representing here are the number of waves they have actually gone through in a certain time t. Now you can see that the first one went up and down 6 times, where the second one, as they're swimming towards the first, actually is going to experience more waves as they move through them, trying to reach the other person. This is, in essence, the Doppler effect. When we have relative motion between the two of them, we are going to experience an increase or sometimes decrease, for example, if it moved this way, in frequency due to that relative motion. So here's one of the examples you can see, and they've actually got this little experiment on their website. In this case, we have a fixed source of sound, and somebody on their bicycle was going to ride along this pathway. They are first going to ride towards the sound and then away from it. So again, they have a number counter of the number of waves that are encountered as the person bikes. Now you can see first, we've got 2 waves that are generated here. In that same time, the person moving towards it has experienced 3 waves. In other words, they've experienced more waves in the same amount of time. That's going to be a higher frequency. And this person moving away has actually only experienced 1 wave in the same amount of time. They're going to have a lower frequency. Thus, the sound you always hear is "nyom." It's always higher than lower. Higher as you move towards it, lower as you move away. Here we can see that we actually have some data. So they've taken the sound and put it into something like Audacity or a similar kind of program. In this first diagram here, we can see how long it took for 25 cycles to be created, and they've created this line right here to stand out. In the second line, they have the data for the bicycle approaching the sound, and now you can see that they've marked off 25 cycles as well, and it takes less time. So the same number of cycles in less time means the frequency must be greater. And then as the bicycle is moving away from the sound, you can now see that it takes even more time than the original one. That means it's going to have a lower frequency. Notice the actual sound doesn't change the frequency. It's how the observer here is perceiving the change in frequency. Now I have here a different kind of diagram because I have a moving source. Now we know that if a sound is created, the wave will travel in all directions from the source, and it will get our circular wavefronts just like here. Okay? Now if I take a look at the red circle, its center is way back here where it says number 1, because it was created first. And by the time we've got 1, 2, 3, 4, 5, 6, 7, that sound has started from its central point and moved as far as that red circle. It's had longer then to propagate, where number 7 has just been released. Now when we do this, that means that the apparent frequency and apparent wavelength is going to be depending on where you are compared to the circles. If we take a look, all of these circles in this area right here are farther apart. That means they're going to appear to have a larger wavelength or lower frequency. So if we were at this position that said observer 2, that means we're going to have higher wavelength, lower frequency compared to the actual frequency that was being emitted. The opposite's going to occur over here. We can see that these wavefronts are closer together, so there's going to be an apparent lower wavelength, which means a higher frequency. And observer 1 is before the source, so the source is still coming towards it. Okay, we see here we've got the data still that supports this. We've got the actual frequency that's being created. The approaching one has a higher frequency, which means it took less time. That's the second line. And observer 2 that has the source moving away from it has the apparent higher wavelength, which means a lower frequency. The reason this is really important is it doesn't matter if it's the source moving or if it's the observer moving, we are still getting the same effect. If the two are coming towards each other, we get a higher frequency. If they're moving away from each other, then we get a lower frequency. So if we can keep that in mind, that it always goes and we have a higher frequency when they're coming together, a lower frequency when they move apart, we can then make sense of these equations. You know, I clipped them from the data booklet. I love my data booklet. One thing students always ask me about is, how do I know whether to use the positive or negative sign here? Whether I add them together or I subtract them? How do I determine that? And again, it goes back to So first we're going to determine, is my observer still or is it the source that's still? So in other words, moving source, I'm going to use the top equation. If it's coming towards me, I need to be creating a higher frequency. Well, the only way I'm going to be able to get a higher frequency is to get that denominator to be smaller. So in that case, I'm going to use V over V minus US. In order to get a lower frequency, I'm going to have to use a larger denominator that's going to reduce this ratio, and I'm going to use V plus US. We can use the same logic for the second equation. So if they're moving toward each other, I need a higher frequency, so that means my numerator is going to be V plus U naught over V. And if they're moving away, I need a lower frequency, which will be V minus U naught over V. So far, we've been talking about waves like sound waves, things that travel through a medium. But what about EM waves? They're a little different. They don't need a medium to travel through, and they always travel at the speed of light. And this kind of gives us a little bit of a pause to think. Well, if it's moving away or moving towards us, then there is no relative speed that we're talking about. So how do we still get the Doppler effect? Because yes, we still do. I have here a picture of a person looking at a distant sun and star through a telescope, and I've got some data here saying, hey, look, we've got a positive velocity, not negative velocity, and it's keep going back and forth. And that's as this planet rotates around this distant star, we're getting this difference. So you might say, well, how would we ever know that? And this is where we can actually get the Doppler effect. And you might have already heard of it in terms of a redshift or blue shift. Now, what we mean by a redshift is that a spectrum line that we know here on Earth has been shifted more towards the red color. And if it's moving towards that end of the visible spectrum, it's implying there must be a longer wavelength or a lower frequency. That would imply whatever was giving off that light must be moving away from us. This is the idea of the universe expanding. So what does a blue shift mean? This would imply a shorter wavelength, higher frequency, which means whatever I'm looking at must be moving towards me. This is a good time to note that the Doppler effect we can see now is not just sound waves, it could be light waves. And they also use this, for example, if you're using the ultrasound. They can actually do ultrasounds to look at your heart or even your kidneys to see whether those fluids, blood or urine, moving towards or away from the machine the doctor is using to see the signal. So let's see how the use of light, which travels at the same speed regardless, compares to our sound equations for Doppler. So on the left I have the ones for sound, and on the right, yes, I clipped them from the data booklet as well, we have the ones that are only valid for EM waves. Now I point that out because it's not just visible light. It could be for radio waves or microwaves. So if we were talking about using radar and speed traps, things like that, it would have to use the equation on the right. So what does it say for us? It says the fractional change in the frequency is the same as the fractional change of the wavelength. So here, in order to get the fractional change of the frequency, I would have the amount of the shift of the frequency compared to the original value, likewise for wavelength. And that is going to be approximately the same as v, that's the relative motion between the two of them, compared to the speed of light. Okay, so let's try a couple examples. First of all, we've got one here. The ambulance siren emits a sound frequency of 1,200. We've got the speed of sound, and it moves towards us at a constant speed of 40 meters per second. What is the frequency heard by of the observer? Now, it says stationary observers, that means a moving source. Make sure you take the correct equation. So we're using the ones for sound, and stationary observer means a moving source. And it's moving towards, so you can see that I use the minus sign underneath so that my ratio is bigger than 1. Now this is one of those questions that you can do without a calculator on a multiple choice. So they're looking for you to substitute in the right values. So my frequency starts off as 1,200. My velocity is going to be 330. That's what v is. And us, the speed of the source, is going to be 40. So if I do this and I calculate it in here, I'm only going to get one possible answer. Notice if you had have chosen the wrong denominator, that answer is here too. If you had have chosen the moving observer rather than the stationary observer, the other equation, that's there too. So they're looking for you choosing the right equation and putting in the correct data. So a motorboat vibrates in the water, so it produces water waves at a frequency of 0.2 hertz. The speed of the wave is 20 meters per second towards a stationary boat. And the boat moves with a speed of 5 meters per second. As I pointed out earlier, the Doppler effect can be used in a lot of different situations. Sound waves, light waves, and now they're showing you water waves as well. So, what is the frequency which the waves hit the stationary sailing boat? So that means I have a moving source again. As well, we also know that it's moving towards, so I should have a higher frequency than is emitted. So there's my equation again for a moving source moving towards us. Again, I'm going to use the minus sign on the bottom so that I get a larger frequency being created. So let me just put in some values. And if I start to calculate this, 0.2 times 20 over 15, and that's going to be 0.2 times 4 over 3, 4 over 3, 1.33 repeated, multiplied by 2, rounded to two different significant figures, and we are going to get answer of D. Okay, so finally here I've got an example with EM waves. We have a frequency of 4.672 times 10 to the power 14 hertz, and the same line observed from a distant galaxy is shifted to this. So first of all, it says state the direction of the motion. Now we can see here that the observed frequency is lower than the original. That means it's must be moving away. Now the second part says deduce the speed of the galaxy relative to Earth. So let's go back to our change in frequency over the frequency is going to be approximately equal to the speed over the speed of light. If I now go and rearrange this equation, we're going to have the speed is going to be change in f over the original f times the speed of light. So let me go and put those numbers in. And once I pick up my calculator, I get 1.93 times 10 to the power 5 meters per second. That's the relative speed of the Earth. And as we just said, that they are moving away from each other. So I hope you take the time to read through the success criteria that I've tried to cover in today's video. I hope this helps.